Welcome to the EPG Patashala, the lecture series in computer science for the postgraduate program. And this is the compiler design course, and we are in the 21st module, which is going to talk about type checking, which is part of the third phase of the compiler, which is the semantic phase of the compiler. So till now we have basically looked at the syntactic and the lexical phase of the compiler, and we've also looked at tools like lex and yak to identify the tokens, and the sequence of tokens is also validated using the tool yak. So with that assumption, the semantic phase has to basically check additional information which is done based on the output of the syntactic phase of the compiler. So the objectives of this module are to understand the semantic phase of the compiler, what is happening here, why do we need all these things in the semantic phase. So that is what is the primary objective, and followed by we should learn about type checking, which is one of the components of the semantic phase of the compiler. So type checking, so your compiler has to verify whether the source program follows the syntactic and semantic conventions. Now the syntactic conventions is basically done with respect to the, is validated with respect to the parser, and the semantic conventions have to be validated by the semantic phase of the compiler, and this kind of checking is basically referred to as static checking. This is in addition to the dynamic checking, which will be discussed in the subsequent modules. This type checking basically helps in reporting programming errors, which is very essential for understanding and correcting the program so that it produces correct result. So static checking, we have basically 4 types of checks that happens for a static check. The first one happens to be type checking, which is very essential compared to all others. Now the other kinds of checking can basically be done by the programmer himself or herself. The type checking is basically done by the compiler. So if the other errors are, other kinds of static check are also validated by the semantic phase, but that is a very simple task in comparison with the type checking that has to be performed by a compiler. So the type checking basically validates whether an operator is applied to an incompatible operand or an compatible operand. So for example, you will have an error if an array variable is added with a function variable. So supposing if I have int a and if I have a function called as void quicksort, okay, so I cannot operate qsort and or rather quicksort with the variable array variable a. So this is what is done as type checking, which is a part of the static checking that has to be done by the compiler. The second check is the flow of control check, that is the statements that results in a branch need to be terminated correctly. So supposing you have a break statement or you have a continue statement which is part of your program, so the you should not leave loose ends in your program. So every path from the beginning of the program till the last has to be terminated correctly, and that is done using what is called as flow of control check. The third static checking is called as uniqueness check, where we will compare whether the object that is defined exactly once for some scenarios. For example, the labels in the case statement. So case 1 we have switch case in the case of C program and Pascal, etc. And so these statements should have unique labels, okay, and the identifiers also need to be unique, okay. So identifiers in the sense that the variables declared should be unique. So that is done in the case of the uniqueness check. The last type of static checking is name related checks, where it will verify whether the same name appears more than once, and if it appears more than once, is it going to be the same in the beginning or at any point of your statement in your program. So at every point of your program, if a particular variable name is used, the consistency should basically be maintained. So that is what we do as name related checks. Now the example here is, for example, if I have int of int and operator of float, so int f of float, int a, c of 10 comma d, d is equal to c plus d. Now what is c and what is d? C is actually an array variable and d is a variable, but c actually refers to the address of the array. C of 0 refers to a data, whereas c refers to address, okay. So I am actually operating an address with the content. So I can actually operate address of d with address of c, but I am not doing that here. I am operating on just C and D. So C is a name of the array which is nothing but an address, and here D refers to the variable D and its content basically. So therefore it is going to be resulting in a failure. The second one is star D is equal to A. Now star D means I am trying to dereference D, okay, but D is already an integer, so I cannot dereference D. So I will say star D is equal to A, that is also going to be a failure. The next one is A is equal to operator of D. This is okay because we are looking at overloading. So operator of float, okay, it is now taking an integer operator here, which is fine because we are looking at overloading, and that value is assigned to A, that is also fine, and A is equal to f of D. So this is called as coercion. We will see what it is. It is a type conversion basically. Vector of int v semicolon. So this is a declaration for the function vector whose argument is an integer and whose variable is v, and this is okay because this will result in templates in C++. So on the other hand, flow of control check. So I have a function called as my function, and the body of that contains a while loop, okay, whose argument is n. If I is greater than 10, I break. Okay, this is fine because I have only one statement here, and I will come out of it without any difficulty. Now on the other hand here, if I do not have the while and if I simply do a break, so without branching I am trying to break. So where will it go after a break? That we do not know. Normally when a break is encountered here, where will it go? It will come outside the while. So this break is part of the if, okay, it will come outside the while, that is what we are looking at as break. So this is fine. On the other hand here, the break is, there is no reason for a break here. This is an unnecessary break without validating a loop construct or a any conditional construct. So therefore this is going to throw an error as flow of control check. Then uniqueness error, uniqueness check, I have here I comma j comma I is repeated twice, therefore this is going to throw an error. And here again C nufym, this is a function name. So int a comma int a, so the same argument is given twice, again it is going to throw an error because this is expected to be some other integer, okay. So that is what we are looking at as type checking. So in this module we will be looking more detailed about the type checking rather than about the other flow of control checks or the uniqueness check or name related checks. Name related, all these things can basically be identified easily as compared to type checking. So where will the type checker be available in the flow of the compilation process? So we already have the parser which is going to yield me a syntax tree. Okay, now that syntax tree will basically be fed as an input to the type checker. The type checker will verify whether the syntax tree is correct or incorrect for a particular input, and it is going to retain the syntax tree structure itself, and that is given as the output. So input is also a syntax tree, output will also be a syntax tree. This type checking will basically done with reference to adding so many semantic rules as part of the grammar corresponding to the programming construct. So we already know what is going to be the grammar of a particular programming construct. Based on that grammar we will write semantic rules, and those semantic rules will basically perform the job of type checking, and then that is given to the intermediate code generator. So this is fed to the intermediate code generator. So it is just occurring just before the intermediate code generator, whose input also needs to be a syntax tree, and the output of the type checker is also going to be a syntax tree. So as we know, this is carried out in semantic phase. Type checking information added with semantic rules, and basic type checking is performed, and this is extended to type checking of complex attributes also. So we will first start by verifying whether an integer should be an integer or a real number should be a real number, and then we will carry out for additional statements, declarations, etc. So let us look at the type checking of expressions. As we already know, the expression grammar can be E produces ID, E produces here literal, and here I am talking about E produces num, which is going to be a integer, and some example here. Now how do I write semantic rules? So these are your semantic rules here. Now this semantic rule will, as we see, the semantic rules are based upon assigning attributes to your non-terminals, and the non-terminals can have attributes like type, place, value, address, etc. And here for type checking we are concerned about the type of the variable. Now what does the first one say? So this is the semantic rule. E dot type is equal to char is a semantic rule which is appended as part of the for the particular production E produces literal. So here I say E dot type is equal to character. Now this is the terminating statement for any particular non-terminal. So therefore for these things, these are called as basic type statements. Okay, these three are called as basic type statements, and these are actually constructed type statements based upon the basic type statements. So here I have E produces num, which says E dot type is equal to integer. So number can be an integer. That's what is my assumption here. So it checks now when an input comes into picture. If I have value 5 here, then it will check whether 5 corresponds to an integer or not. So 5 is an integer, therefore it is going to say okay. On the other hand, if I probably going to have this production, and if I have 5.22, it is probably going to throw an error because it is not an integer, it is going to be a real number. Now how do I handle that? To handle that, I can either do what is called as a conversion, which can be a implicit type conversion or an explicit type conversion, where I would truncate the real number and convert it to an integer. That is one option. Other option is I am expecting an integer only. If you are giving me a real number, I will throw an error. So that is going to be the next option to get rid of this. So again, it is the semantic rules are written by the compiler designer. So therefore, whatever is required or whatever is necessary can basically be incorporated here. The next one is E produces E1 mod E2. Now I have to assign the type for E, the left hand side E. So I am renaming this as E1 and E2 because I just want to differentiate this E from this E and vice versa. According to the production, it will be simply E produces E mod E, but to differentiate which E I am referring to, I will basically be in a position to distinguish that. So using the suffix 1 and 2 respectively. Now what do I do that? It's a mod operator. Okay. So I can compute the mod only if E1 is an integer and E2 is also an integer. Correct? So if E1 is an integer and E2 is an integer, I can compute the modulus of these two integers, and what will be the LHS, what will be the return, what will mod return basically? Mod returns the remainder of E1 and E2 after division. So the LHS will also be of type integer. So how do I formulate that as a rule? So the rule formation here is, if E1 dot type is equal to integer and E2 dot type is equal to integer, now only in this scenario I can basically perform the mod operator. So the mod operator resultant will be a reminder after computing division. So therefore it is going to throw integer as a return type, and that is assigned to the LHS expression E as type. Okay. So this is what we do. So left hand side type is nothing but, depending upon the validity of the types of E1 and E2, the LHS will be assigned a type, either in this case integer, or if this is not satisfied. For example, if E1 is real and E2 is going to be an integer, or vice versa, or both are real or both are characters, something like that. So therefore, in that case, this will not be satisfied. Therefore, I will simply return type underscore error, which is a defined type, which is nothing but an error type written by the user, that will be returned to the type, and that will be assigned to E. So you will check the type of E. If it is of type error, then we know that something wrong has basically happened. So that is how you basically validate and correct the errors later after type checking. Continuing on this, so E produces E1 of E2. Now E1 is the name of the array and E2 is going to be the array index. So what am I expecting here? E2 should be number. That is what we are trying to look at very specifically. That is, I have to say A of 10, okay, array of 10. I have to declare some number there. So what will I say here? If E2 dot type is equal to integer, and if E1 dot type is equal to array of S comma T, okay, array of S comma T, which is a mapping from S to T, then you return T as return type, else you return type underscore error. So this is the next one. Following that, we have if E produces E1 up arrow. Now this is a Pascal syntax. So the up arrow basically refers to, it's going to be a pointer variable. So what am I looking at here? If E1 dot type is equal to pointer of t, okay, pointer of some integer, okay. So for example, if t is of type integer, then LHS will be of type integer. If t is of if this t is of type real, this will be of type real, and so on and so forth. That is where it is pointing to, that will be returned to the LHS variable. So here I am checking whether E1 dot type is equal to pointer of t. If that is true, I will return t, okay, else I will return error. So that is on with respect to type checking of expressions. Now the next one is type checking of statements. Statements can basically have a type void if the statement is correct, or it will have a type as error if the statement is incorrect. Okay. Now let us take the a simple example here. S produces ID colon equal to E. So this is the simple production where LHS is going to be a terminal and RHS will be an expression. So this is a typical scenario. So what will I check basically here? If ID dot type is equal to E dot type, meaning that this expression, okay, will return a type. Why? How? It will return a type depending upon how we have already assigned. So if both operands are okay, the previous example, the previous type checking statements assigned a type to the LHS expression E. Now this is going to be available as the RHS of this particular statement. So ID colon equal to E will be, this E will refer to the expression which we have already encountered. It could be arithmetic expression, in this case it's going to be arithmetic expression, or it could be some logical expression computation or whatever it is. Now if E dot type, that will be assigned to ID dot type, okay, if that is true, then S will have a type as void, else it will have a type as error. So if these two types basically matches, then this type of S will be void, else it will be error. The next one is if expression then statement. So we know that this is a simple if construct. Again here type of S depends upon whether this expression will be a boolean, because you are validating whether it is boolean, then you will go into S1. If it is not, you will basically stop. Okay, if expression then S1, in that case S dot type is equal to, that is LHS S is equal to, if E dot type is equal to boolean, then whatever type S1 refers to, that will be assigned to this S, else you will throw an error. Okay. So this S will have a type only as void if the RHS is going to be a correct production. Okay. Continuing on this, you have a while expression do S1, S dot type is equal to, if E dot type is equal to boolean, then S1 dot type, else type underscore error. Okay. So this is again similar to the previous case only. Again, if it is going to be an if else, how do I write it? Again it will be if E dot type is equal to boolean, then S1 dot type, or I can even say if E dot type is equal to true, I can say it is S1 dot type, else it is S2 dot type, else it is going to be false, type underscore error. So that is going to be your scenario. So if it is true, you will return S1 dot type, if it is false, you will return S2 dot type, and if it is going to be anything other than true or false, if it is something else, you will throw an error. So now we can use that as a scenario. If expression do S1 else S2, in that case we can assign S1's type or S2's type. So it will normally fall into these two categories only. So that is why we have not looked at that as an example here. And the last one is S produces S1 semicolon S2, that is a sequence of statements are existing. In that case I will return S1 dot type is equal to void, and S2 dot type is equal to void, then void, else type underscore error. That is if this is also void and this is also void, then we will return void, else if this is error or this is an error, I will return the error as my type for the LHS S. So this is type checking of statements. Now the next one is type checking of functions. So where I will have a function call E produces E1 of E2. Okay. So the LHS type is nothing but if this is going to be, if E2 dot type is equal to some S, okay, and E1's type is a mapping from S to T, if this mapping is justified, then you return T as a return type, else you return error. Now it is a function, so it should play with the arguments and then get some value computed. So therefore we are explicitly stating here if E1 dot type is equal to S arrow T, that is a mapping from S to T, then we return T, else we return type underscore error. The last one is T produces T1 arrow T2, okay. T1 again a function mapping T1 to T2, T dot type is equal to T1 dot type arrow T2 dot type. So that is what we basically refer here, okay. So this is on functions. So now type checking is the primary characteristics here, and in addition to type checking we are also going to do what is called as coercion. Coercion refers to implicit type conversion done by the compiler, okay. This is done with respect to computing arithmetically two operands, okay, and if both are of different types, how do I handle it, okay, or rather looking at the incompatible operands, okay, and then can compatibility be established or not established, that is what we are looking at as coercion. So implicit type conversion is called as coercion. Normally explicit type conversion is also done by the programmer, where the programmer writes the code as int of some variable a, that is treat a as an integer or truncate a to an integer, okay, or we normally say a divided by 5.0, where you are looking at as a divided by 5 could be your computation, but we want to have the decimal component also. So therefore what we do there, we will do a divided by 5.0. So that will be considered as an explicit conversion done by the programmer, okay. So for coercions, this is going to be the same as we already know. So num is type integer, num dot num means I am talking about as a real number. Again this is Pascal, therefore we call here as a real as compared to float in C. So E produces ID, in that case type of E will be depending upon what is looked upon in your symbol table, and if I have E produces E1 operator E2, type of E will be, if E1 dot type is equal to integer and if E2 is also of integer, then you return integer, else if one of them is integer, other one is real, you return real, okay. So either E1 could be real or E2 could be real, in both cases also you will return real as a return type. If both are real, you will return real. If it is not falling under any of these categories, you will basically look at returning error as the type information. Now what is happening here? If both are integer, no problem. If both are real, also no problem. If one is integer and other one is going to be real, I am permitting it to perform some operation here, but I am converting the resultant of the operation to be real, okay. That is why you normally get a warning if you do incompatible operands to perform some computation in your piece of code. So here if one is real, one is integer, you normally return a real, because this particular piece of semantic rule permits you to compute one operand followed by the other operand, okay, but it is considering that as a real number as against an integer. It is not truncating, it is considering that as a real number. So that is going to be the end of type checking with reference to coercion as well as with other things. So after type checking, okay, after type checking, my front phase of the compiler is basically done. I am done with my front phase, that is the analysis phase is done. I have tokenized, I have verified the sequence of tokens, I have added type checking information, and I have basically looked at how the code is going to, how the representation is going to look like. And not only that, we have also converted this into what is called as an abstract syntax tree, okay, as against a derivation tree which we have already got. So using syntax directed translation. So type checking is also added as a semantic rule for every programming construct which is based upon the context free grammar defined for that particular programming construct. Now with that in mind, we will now move on to the next phase of the compiler, which is nothing but the intermediate code generation. Now the intermediate code generation gets input from the front end, it is going to basically stay right here, okay, and that is given to the back end to generate the target machine code ultimately. So this is what we have here. So the front end is connected with the back end using the intermediate code only. Now why do it facilitates retargeting? So it enables attaching a back end for the new machine to an existing front end. So front end basically is language dependent, but we have not even touched upon even a single instruction or a single message is looked upon the target machines features or the characteristics or how do I generate the instructions. Nothing has been looked upon. We have so far simply analyzed the piece of program which was given to us. So the intermediate code tries to connect or convert this front end to what is required or how is required by the back end of the compiler. It enables machine independent code optimization also, that is the functionality of the intermediate code generator. Now there are various representations. So this is what actually your syntax directed translator basically does. The first one is you can have graphical representations where you have an abstract syntax tree, or I can have a postfix notation where there is operations on values stored on the operand stack. Example is JVM bytecode. Or I can basically have a 3 address code representation. So the graphical abstract syntax tree representation, or I can have a postfix notation representation. Postfix notation, again I can have a binary tree constructed, I can do a post order traversal, or I can simply have a postfix expression itself which is generated by converting a normal expression to a postfix notation. Or I can have the intermediate representation which is going to be what is called as a 3 address code. When I have a 3 address code, I am permitting till 3 addresses. That is what we basically talk about here. Now let us take this example. We have already looked at this, a part of it in the previous module, where we are trying to do a syntax directed translation of abstract syntax trees. So again that is based upon the production and it is based upon writing a semantic rule for the same. So for this I am trying to create a node pointer for the variable s, which is nothing but using a function make node whose operators will be the assignment operator, and I do a make leaf of id, and there is going to be one more e which is going to be again an address, again a node. Okay. So if I basically have e produces e1 plus e2, e dot node pointer will be make node of this basically. That is, I am creating a new node whose LHS will be the node of e1 and RHS will be the node of e2, and both are connected using the operator plus. So similarly I can write all these rules, and this is one way of representing your derivation tree to a syntax tree representation. So this is the way as abstract syntax tree is basically represented. Now this is what has been shown graphically. So e produces e star e. I can look expand this as a derivation tree as e produces e star e, and then parenthesis e close parenthesis. Again the inside e is nothing but e plus e. Okay, where this each e corresponds to a, b and c respectively. This is the corresponding representation for this particular syntax tree whose LHS. So the star node is here, LHS is a, RHS is a plus node which is e dot node pointer, right? That e dot node pointer again is going to be a node whose operator is plus, whose LHS and RHS are going to be b and c respectively. Now abstract syntax tree is one way of representing your intermediate code. The second way of doing it is using what is called as a DAG. A DAG is a directed acyclic graph. Okay. So this DAG is a beautiful intermediate representation which is going to help in optimization also at the later stages. So for example, this example is going to be carry forwarded for the subsequent module also, which is given in the textbook Aho Sethi Ullman. So a is equal to b star minus c plus b star minus c. So if I expand this, it's going to be some b plus b, or rather expression plus expression. So I have expression, expression plus connected, and id colon equal to expression, which is again a node pointer. This is nothing but again expression multiplied by another expression, expression multiplied by another expression, and this expression will be a negation of another expression. Okay. Now I can represent this in a concise form in a DAG where this is a common expression. B star minus c is a common expression. So I can use that here, b star minus, that is I can join them as b star minus c here, and this node operator, this plus operator here has an LHS pointing to the same computation, RH is also pointing to the same computation. So b star minus c is computed here, I am adding those two, okay, and that is resultant of this particular node. Okay, so this is one way of representing, and this is the rules for creating DAG. Again, it is nothing but looking for the commonality and then trying to generate. So again here E plus minus node, E node, all these things are same except for the fact that you are trying to look for commonality here. Okay, is it already available? Now there is one more method for constructing DAGs, one more representation for DAGs is the value number method, where supposing if I have some I is equal to I plus 10. So I is equal to I plus 10, the corresponding DAG will be something like this. So I will say here num corresponds to 10, ID corresponds to a address of I, and I have to add 1 and 2, that is this refers to 1, this refers to 2. It's a table based, it's an indexing based approach. Okay, so the first row corresponds to index 1, second row index 2, third row index 3, and so on. So I have to add the the contents available at index 1 and index 2 respectively. That's what this basically say, and using the operator plus. And what does this basically say? This is 3 here, 3 is this particular statement, and one operand is 1, the second operand is 3. That is the first one is ID, second one is the content of this particular stuff, it's assigned to 3. So that can be one more representation of the DAG, which is a table approach. Now this is a small algorithm for that. So search the array for a node M with label operand, L child and R child. If there is such a node, return the value number. If not, create a new array node and then a label with the left and the right child and return its value. That is going to be the algorithm. So we can use a hash table here. This we will be looking at. Example of this also we will be looking at it in the next module. So on summarizing, this particular module looked at some static checking types as type checking, flow of control check, uniqueness check related, and name related checks, which are part of the semantic phase of the compiler. This module also introduced the ways of intermediate representation in a particular compiler basically, and the ways of representing in terms of syntax tree, DAG, or the 3 address code was basically introduced in this module. Thank you.